Hello, it's Keith here, and this is lesson 7 of the YQuest series, in which we're looking at porting the YQuest game, which was originally written on the Amstrad CPT, to various other systems. This time we're looking at the Master System and the GameGear. You can see the game running just here. Now the only slight difference on this version is we're unfortunately using the tile map, which means the movement is a little bit jerkier than on the CPC, but I think the game is still pretty decent anyway. And the other benefit of this is we're actually able to compile it also onto the GameGear. Where is it? And with a few tweaks we're able to play it. Now it would be a little bit more difficult because the screen's smaller. Now at a later date I might convert this and I might add it so it uses hardware sprites rather than the tile map, but the version we're looking at today was just a quick port and it uses the tile map, so it's not as good as some systems like the Sam Coupe, for example, which is a 16 colour screen and uses a bitmap screen, but I think it's a good enough starting point for a simple example for a beginner writing a game. Okay, so we're going to go over the source code today and we're going to learn how it's been ported to this system. The code we're looking at today is just the platform specific code. The multi-platform code we've already covered in previous episodes, so please take a look at those for the bits that we're not covering today if you've not seen them. Right, the first thing we're going to be covering is these collision masks here. Because we're using a tile map, we're having to limit the position of our sprites to an 8x8 grid. And because of that, some of the collisions might be a little bit iffy. For example, if our sprites were partially overlapping on the previous systems, that would have been allowed on the CPC, but you're not going to be able to tell if they're partially overlapping or not on a system like the Sega Master System. So I'm masking out some bits of the XY position for the collision detection to make sure the collision detection is being checked at the same definition as it's being drawn, because the internal workings of the axes are at higher definition than we're drawing in this case. So that's just to fix that. Then we've got some definitions for the Master System and the GameGear. The screen size is of course very different. Either way though, we're using the same address for the memory. The game needs some RAM and as well as the ROM. So the ROM is the game code and the sprites, but the RAM is the positions of objects and scores and things like that. So we're defining an area of RAM here for the game, and that's in the multi-platform code we looked at before. Then we've got the header of our program here, initializing the screen, defining the palette, we've covered all this before, and transferring the sprite data into the pattern definitions that we're going to use for the tile map. Now here we're just clearing out the user RAM just in case there's any junk there, and then we're starting the game with the title here, setting the number of lives, resetting the level, resetting the player object, silencing any sound, and clearing the screen here. Next we're going to show the title to the screen. That's this code here. And what we're doing here is we're reading in each byte of the title. The title will be different depending on the screen size. That's in the multi-platform code though, in the data definitions. So we're using that, and there's two versions for the Master System and the GameGear. What we're doing next is we're reading in the sprite. If it's not 0, we're going to show it to the screen. We've got to add 96 though, because the first 96 patterns are actually the font. So we need to skip past those to the actual characters to draw the title screen. Now we're having to use different comparisons depending on the screen size, because of course the GameGear is a much smaller screen, and then we're showing bits of text to the screen again in different positions depending on the system. So we've got the fire message, the URL, and the high score here. Just depending on the system we're having to relocate to different positions depending on what looks good on the screen. Here's the start of the game though. We're waiting for a fire button, clearing the screen, recentering the player, and loading in the new level data. All of these are handled by the multi-platform code. Next we're running a read joystick routine, which we'll see later on, which is reading in the input for the directions, and it's going to store it in D here. We're looping until our counter's expired, and if we want to slow the game down we just increase this counter. If we want to speed it up we just decrease the counter. Pretty straightforward. And then here we're starting to draw the player. So first of all what we're doing is we're removing the old player position here from the player object. Now the player object contains the XY position of the player. Before that we're just drawing the user interface to the screen. That's the score and the lives and things like that. Next what we're doing here is we're loading in the key timeout and checking if it's not 0. Now when we hold down a direction we're increasing the acceleration of our movement, but if we accelerate too fast then we'll quickly lose control. So the key timeout will ignore the holding of the direction for a short period before processing it again and increasing the speed again if it's still held. So that's what we're doing there. We're then processing the keys of D, which we loaded in from the joystick earlier. And so these bits are the up, down, left and right, and we are just altering the current acceleration accordingly depending on which direction is pressed here. Now, when we get here, we're just checking the fire button and firing a bullet if the fire is held down. This is, of course, multi-platform code. And here we're zeroing the acceleration if fire 2 is held down. So if you press fire 2, you can immediately stop. You've got a kind of handbrake stop there, so you can do that. And if one of the directions was pressed, we've set E to 5, and we're updating the key timeout here if one of the directions was held down. Next, we're updating all of the sprites, that's multi-platform code, and here we're just repeating, and that's basically the main game loop for the platform-specific code. Just really very little other than the input, really, because the rest is all multi-platform. This routine is handling the sprite font for drawing text to the screen. The first 32 characters aren't represented in the font, nothing below space is in there. And then what we're doing is we're loading the XY position of the tile for the current character. Cursor Y and cursor X are immediately after each other. So C is cursor Y and B is cursor X here. And then we're using the show sprite routine to do the work of drawing the sprite to the screen. Show sprite will show a sprite that we've specified, and do get sprite object will calculate the sprite number from the IX register that's been passed to it. So that's used for drawing things to the screen, like the player and like the enemy objects and things. Now we've got the sprite frame. There's 4 frames of animation, and we will cycle between them. Now there's 16 sprites for each bank, so we're just having to multiply that up here so that we move it into the right position, and then we're adding the sprite number to that, and that is giving the sprite within the patterns that we want to show at the tile position. We're then needing to take the X and Y position, convert them to a tile position, because the X and Y position internally are much higher resolution. They're designed for a bitmap screen like the Amstrad CPC, or ideally the Sam Coupe. The Sam Coupe is the ideal screen for the internal format of these. It's 2 pixels per byte and 192 lines. That's kind of perfect, but in this case we're using a low resolution because we're using the tile map, and then we're calculating the screen position and we're showing the tile to the screen. This is all kind of similar to what we saw in the simple series where we drew the bitmaps to the screen. This is the blank sprite routine here. What we're doing is we're using the space character and we're showing that to the screen to remove the previous character. Here we've got a clear screen routine. All we're doing is we're setting all of the tiles to tile 0 here, just to blank them out. Define tiles, we've seen that before. That's just transferring data to video RAM. That was in the simple series, so please take a look at that. As was get VDP pos, that's just calculating a tile position based on an XY position. Here we've got our font. Here we've got our 4 frames of animation for the sprites, and they're all in the bitmap data range here, and they're all transferred to the pattern memory within the system. Read joystick will read in the direction keys that was used earlier, so we're loading in from port DC, which is up, down, left and right here. We've got this wait for fire routine. What this does is it reads in from the joystick, and it waits for the fire button to be released and then pressed, and this is a debouncing so that we can have a press fire to continue to next level thing when the player continues or when the player dies. And all the time that we're waiting, we're randomizing the random seed again, which is just updating the random number generation to make things a bit unpredictable. Okay, here we've got our multi-platform code and our common code that was done in other tutorials. These are handling things like the sound, the common code for handling the player movement, the enemy movement, things like that. And then finally, we've seen before, we've got the initialization for the screen, the palette. This is all very similar to the simple series we covered before. And finally, the footer, which defines the actual cartridge header, if you will, at the bottom of the cartridge. That's really all there is to it. So there isn't actually very much in these platform-specific lessons, and that's the intention. Ideally, we want our code to be as small as possible, so we have as little as possible to port. Now, most of these platform-specific versions I've been able to port within 30 to 60 minutes, and if I'm honest, the time that it's taken more than 30 minutes is usually because I've made some embarrassing mistake. And that's the sort of benefit of having as much of your code multi-platform as possible. I wrote originally on the Amstrad CPC, but when I designed it, I made as much effort as I could to make sure it would be easy to convert to other systems, because I have a reasonable understanding of what those other systems' limitations are and how I can design my program to be as not platform specific as possible. Anyway, if you've enjoyed this, please like and subscribe. It helps with the ranking in the YouTube search. And also please go to my website and download the sources 7-zip from the Z80 site, which will contain all of the code for this today. You're welcome to modify it, mess with it, and hopefully make something better than I managed. So good luck with that. I hope you enjoy your programming, and I wish you a lot of success. Thanks for watching today, and goodbye.